Hello everyone. Today I'm here to present my final project report 5560 Recurrent Neural Network for Sequence Data. My name is Amita Reddy Pedreddy. My student ID is 11605342. In the first page here you can see the table of content, like what all parts that I did in the report are mentioned here. So in the part 1, a time series dataset has been chosen on my own, and the simple RNN with the sine wave data, LSTM cells for the part 3, what all discussed in the course, and LSTM neural network with the time series data. A new dataset has been chosen, a stock dataset, and the redesign of the same dataset with the LSTM neural network to improve the performance, and comparing the network performance of both the results, understanding of the simple RNN and LSTM models overall, and below is the YouTube link of this video. Coming to the part 1 time series data set, I've chosen the Dallas police arrest data set. It's in CSV format. Here is the reference to the data set. You can go ahead and check in the website of the Dallas police arrest data set. And here is here is a website to the Dallas police arrest dataset. The dataset consists of 65 columns and 104K rows. And the last updated is December 10th, starting from October 13 to 2021. It was a daily updated dataset. The reason why I have chosen and why I believe this as a valuable resource for the time series analysis is like I'll give a complete scenario about example by considering the example. So consider few data fields like AR arrest data and AR time slot and the Dallas police arrest data set. So by to uncover the time series patterns related to the frequency of the arrest during different times of the day. So to consider this, let's go ahead with the specific month and the year from the data set. Choose May 2023 to understand how arrest varies over the course of the day during this month. So the main reason and the conclude this as a time series data set is like with the help of this data set we can analyze patterns through a time series lens provides valuable insights and the temporal patterns of arrest. So with these patterns empowers law enforcement to optimize their strategies, allocate resources effectively and respond proactively to ensure public safety. Out of 65 data fields, I have chosen only 12 because it's completely related to the time series pattern. So what all required, I've chosen these. Coming to the part 2, simple RNN with sine wave data. Simple recurrent neural network. In the world of neural networks, simple RNN takes center stage, especially when dealing with the rhythmatic dance of the sine wave data. This network shines in capturing and understanding sequential patterns, making them ideal for tasks where past information matters. The key components of it are like architecture, formulas, and the memory retentions and applications. Simple RNN consists of an input layer, a hidden layer, and an output layer. Each point, the sine wave sequence becomes an input with assigned weight determining their impact. The magic happens in the hidden layer, and here is a twist: the output gets looped back into the network, letting it remember what it has been seen before. And the memory retention of it is like the ability to retain memory in what sets simple RNN apart. The memory recalls is perfect for handling sequence where the order of the events matters, like in sine wave data. And there are like two formulas for it, the forward pass and the softmax function. The network calculates the total loss for the input sequence. It's like checking how well it's doing in understanding the ups and downs of the sine wave data. And therefore the softmax function is wells like a mastery of conducting the probabilities of different points in the sine wave as a network way of saying. So coming to the code part of the simple RRN with the sine wave data. For this, I have used the GCP for the code part. Coming to the code part, importing libraries has been done by requiring. Coming to the coding part, I have used GCP for the coding, and so firstly, I imported important libraries required for constructing a sine wave generation model. The min-max scalar, along with the Keras and the TensorFlow libraries, has been imported to facilitate the development of our project. Um, so in this project, I utilized a sine wave with 600 data points ranging from 0 to 82 with the help of NumPy space function. These data points are divided into 0 to 82 with each x value having 600 corresponding y values determining through trigonometric function. And then going to the build and train section. So in the build and train section, a two-layer architecture is implemented featuring a simple RNN layer with 82 neurons followed by a fully connected neural network dense. The sequence length is set to 50, enabling the predictions of the 51st value in the data set. To prepare the model for training, a compilation involves setting the loss function for a mean square error and utilizing the Adam optimizer. So going to the evaluation part, so this chart illustrates that initially the loss is at highest. However, as the model undergoes training across different epochs, there is a substantial reduce in loss, ultimately converting to nearly zero. This observed pattern signifies a pivot factor in the modeling process, highlighting the model ability to effectively learn and adapt to the underlying dataset patterns. And in the evaluation part, a new column labeled prediction has been introduced in the modified dataset. The accompanying identifies dataset before and after, showcasing both actual and the prediction part value. Um, this is the as this part is before, and this one is the actual prediction part. So in the of the medal prediction relation to its true value in the data set, allowing for a comprehensive assessment of the model forecasting accuracy. So in the below plot, as the code depicts, like data underscore test dot plot with a flag size of 12 to 8, visually compares the size of the actual sine wave values with the model prediction. Here, the blue line indicates the sign and the orange line indicates prediction. This prediction closely aligns with the actual sine wave at almost all instances, indicating that effectiveness of the modeling in making actual predictions. However, you can see a minor deviations between these lines is observed, possibly attributed to the discussed loss values. This visual assessment undergoes the model overall success in capturing the patterns of the sine wave data. Coming to part 3, LSTM cells. The first topic is vanishing. Let's start with the part 3, RNN and LSTM cells. So starting with the problems, let's decode the mystery of the vanishing gradient problem first. This vanishing gradient problem, it's like a passing a message through many friends, but each time the message gets quieter. What they're saying is like, every time if I send, for instance, if I send one message to one person, it's going to be like quick up-to-date message. If I send the same message to more people, then it might be a chance, there might be a chance like few members they might receive or few members they might not. So it's the same thing that works in the deep neural network. This happens when the learning signals become almost silent as it travels through many layers during back propagation. So the tail unfolds. The problem to this solution is explanation says, as the signal journey backs it multiple times with each layer weights, if those weights are small, less than 1.0, then signal diminishes drastically. So these are the signals and these are the sigmoids. So to address the issue, a straightforward solution is to opt for activation function like ReLU, which does not diminish derivations as the layer progress. And also, if it is like the problem arises only when it is a large input size is compressed into a smaller one, causing derivatives to vanish. So let's get a clear example by giving a proper visualization. Imagine the original message size is 0.5 and passing through layers with small weight values like 0.8. After 10 layers, the message is barely audible at 1.7 E. So as you can see, the original gradient of 0.5 becomes vanishingly small 1.7 into 10.4. After propagating through just 10 layers, this mutes early layer learning, hindering effective updates and severely limiting the model capability, especially in deep or recurrent neural network. So we can conclude that by saying the vanishing gradient problem is like a message fading away through layers. Solving it is a key to ensure meaningful learning in neural networks. And let's solve the second problem, exploring gradient problem. So let's unravel the exploring gradient problem. It's like cooking with too much spices, things get out of control. So let's give like another illustration viewpoint. If consider there's like one box and you put one ball in it, so then gonna be like not bad, the weight is not being going to be the same, like it's like not too heavy. If you put like so many balls in the small box, then it's going to be like heavy, it's going to be explode, it's drop down. So to mitigate these steps during back propagation, gradient can grow uncontrollably, turning a stable model into a wild, unpredictable one. So the scenario for it is like if the gradient journey encounters layers with weight matrices having Ignile values greater than 1, like using too much spices, the value explodes exponentially. So let's consider the example to it. Imagine starting with a small gradient of 0.5, passing through layers with Ignile values like 2, 3, or 1. The final explosion happens, turning the small 0.5 into a whooping 6. So what are the consequences that might occur for this question is like the exploding gradient leads to gigantic updates in neural network weights, making predictions unstable and behavior unpredictable. Mitigation strategies. Strategies for this is like careful weight initializations and gradient clipping or tactics to dam this explosion, particularly recurrent neural network, are more susceptible, especially with longer sequences. So we can conclude this by saying the exploding gradient challenge is like spice overdose in cooking. Managing it is a secret recipe for stable and effective deep network training. So the main solution for this is like the managing. Managing is a secret recipe for stable and effective deep network training. And let's come with the LSTM. LSTM is like hero of the neural network. And in our course that we learned that LSTM is a superhero that conquers both the vanishing and exploding gradient challenges, while also upgrading from simple RNN limitations. So below are the limitations of the simple RNN neural networks. So in RNN neural network, it enables to learn long-term dependencies. Simple RNN can only look at current input XT, that previous hidden state HT1, making predictions. They lack mechanisms that store longer content. And they also lack computational power and memory. Simple RNN process one input at a time in a loop. So they process only one at a time in a loop, making it difficult to track long sequences of over 1,000 steps. They have no explicit memory to store relevant past info, forcing them to compress all context into a hidden state. So they cannot easily, and also they'll struggle while capturing the temporal sequential relationships. They cannot easily interrupt meaning from complex sequences such as in nature, language, audio, weather data. Overall, the simple RNN architecture lacks both computational sophistications and memory to efficiency model long, intricate temporal sequences for tasks like forecasting, speech recognition, etc. And below are the few of the advantages of the LSTM with respect to diagrams given and the formulas of it. And let's go with the LSTM neural network, which provides a powerful solution to both gradient problems. So, solving the vanishing gradient puzzle. The constant error carousel, CEC, allowing errors to flow unchanged, the cell state stores info across sequences, eliminating the need for full back propagation, dodging exploding gradients. In dodging exploding gradients, smart gate units, there will be like 3 gates, input, output, forget, regulates information flow. All these 3 gates will maintain the information. So they have the total control to regulate them, preventing unchecked growth. Clip gradients acts as a guardians, stabilizing potential explosion. And overcoming of simple RNN hurdles. The cell state acts as a long-term memory, storing crucial past context. Multiple gating units allowed advanced time series processing. Information addition or removal is selective, thanks to the mighty gates. And let's give an overview of the lure of the LSTM. LSTM can handle much longer sequential dependencies, making them perfect for tasks like speech recognition and text generation with constant error flow, specialization memory, and gating mastery. LSTM stands as the stalwart of deep learning. It is standard as a stalwart of deep learning. In a nutshell, we can conclude that the LSTM isn't just a network. It's the hero we need for unraveling complex temporal patterns in the world of deep learning. So here in the part 3, we can get to know about all the problems and the puzzles for the LSTM and the limitations, advantages, and also the importance, importance and the applications of the LSTM. Let's continue with the other part. Let's start with the part 4, LSTM neural network with time series data. This particular LSTM is suitable for time series analysis. It's a long short-term memory network, stands out in the realm of the recurrent neural network for the adapt handling of sequential data. Below is the architecture diagram of the LSTM. Let's go ahead with the code part. For this LSTM, I have used the Amazon stock price data. The data set use spans from January 2015 to the June 2022. For an extended analysis, I have used June 2022 to November 2022. First, we created a unique dropout time series RNN model. Initially, we imported like essential libraries from Keras using time series generator for the multi-layer perception with a different level. The min-max scaler is employed to scale the data appropriately for a simple RNN model. As I already told you, Amazon dataset from Jan 2015 to June 2022 was taken for the first part. And coming to the data set, it was like it comes from 2015, includes various attributes. An attribute of this shape is a variable which can be represented by a numerical value that describes its volume. When performing statistical analysis on 3 shapes, one can examine the minimum and maximum values as well as their standard deviation. And the split part, coming to the split layer, was like splitting the data into training and testing sets, reserves like taken 0.1 like 10% of the data for testing after splitting the data set for train and test. The total length of the test is 188 and the total length of the train is 1697. In the training the model, I standardized the training and the testing data by applying the min-max scalar, ensuring values fall within the 0 to 1. To train the LSTM model, I established a time series generator with a sequence length of 60 and configuration it to predicting like every 33rd value with the sequence with the batch size of 32. 32 plus 133rd, and moving on to the building the model, I use sequential architecture with LSTM. Additionally, a dropout layer with a 20% is incorporated, followed by a single dense layer. This setup aims to optimize the model for effective training and prediction. And coming to the test, I created a sequential LSTM model with a thoughtful architecture consisting of 3 layers and to mitigate overfitting. Each layer is followed by a dropout layer. And after designing the model, I compile it using the Adam optimizer and mean square error laws. This approach ensures that the model is well structured, addressing potential overfitting issues, and is ready for the effective training and evaluation. Training the most with the 100 epochs, like using time series generator till up to 100, extended the model analysis like forecast future stock price beyond the original data set. And for forecasting, train the model on the as far as an additional 100 epochs for the next data set too. These are the both comparisons of the two. In the retraining phase, the predicted outputs like whatever outputs are notable, the forecasting value for Amazon shows a significant decrease. Observed trends indicating cautions, emphasizing the need for careful consideration before making investment decision in Amazon stocks. These are the depicted ones. The model underwent like another round of retiring the time utilization for the extended data set spanning from June 2022 to November 2022. This graph depicts the validation showcasing the model performance and the last data set, and also both the test set and forecasting the future stock price. The result indicates the successful adoption of the model to the recent data set, instilling confidence in its predictive capabilities of the stock price. So, below are the key parameters that I mentioned, whatever I said, like by using what data predictions are used and how much epoch is used and the batch size, input sequence and everything. In part 5, redesigning the LSTM neural network has been done to improve the performance by taking the same data sets that we have taken for the LSTM, Amazon stock price, both the new and the extended data set. Just go with the code part. I revamped the LSTM model to access its performance by making several changes, and the training and testing data split percentage was set to 0.2, which is 20%, and batch size was changed to 40, and additionally I modified the LSTM layer by increasing the number of neurons to 60. The input sequential length was designed to 61, and also and the batch size for predicting the sequence was set to 40, as I already told you. And to predict the every 41st value in the sequence, this modification were implemented to enhance the model ability to capture patterns and improve overall prediction accuracy. So I'll go ahead and show the results of both the one. So then an observation is done by using both the data sets 1 and 2, predicting and retraining. Below or this one is a graph for the first one, and this one is a graph for the extended data set. And I'll also show you the basic parameters, key parameters, and what all changes that I made you as like in the bullet points. Part 6. Compare network performance by taking the consideration of LSTM model and LSTM redesign model of Amazon stock dataset. So what I did in this project is like taking these two models by analyzing with different parameters to get to know which has the better performance. So notably in part 5, the redesign model exhibits improved loss performance with loss plots consistently at 0, indicating minimum errors in the model. However, like when picturizing these two prediction LSTM and LSTM redesign model, little variations was observed. So as you can see, starting from here, the close and the forecast, both were like same prediction value has been given. And interestingly, despite difference in the number of neurons, like slight difference, the forecast value will both remain essentially the same. This suggests that while the redesigned model showed enhanced loss performance, the impact on prediction accuracy was marginal. So, by finding highlights the importance of evaluating multiple aspects of model performance to draw meaningful conclusion. So let's go with the seventh part, understanding of simple RRN and LSTM models. So these two models, and I'm going to give you the overview, like whatever I understand from this project, RNN and basics. RNNs are like the memory wizard of neural network, remembering past input using a hidden layer. They're perfect for tasks like predicting the next word in a sentence. And they're good in memory wizards and neural network, and they're like damn good in remembering past inputs using a hidden layer. And coming to the LSTMs, a superhero among RNNs. So it's a comparison between these two, designed for tasks needing long-term memory. It uses special gates to decide what's important and retains crucial data over time. So what's this LSTM do is like it uses a special gate like to decide which one that should be holding like and which one should be removing from the information. And the time series forecasting, here comes the time series forecasting. This was like thinking of forecasting as describing patterns in sequence. RNNS believes in processing the entire sequence for context, but LSTM steals the show with their ability to manage long-term dependencies crucial for sequential tasks. And LSTM handle the vanishing gradient problem by using memory cell and gates, allowing selective storage and retrieval over extended periods. LSTMs are nothing but they were like rock stars in the speech recognition and image caption, thanks to their enhancing features like attention mechanisms. So all these speech recognition, image captioning of all this will come under the LSTM applications. And so let's compare the RNN versus LSTMs. RNNs are the basics, LSTMs are the advanced version with separate cells. States for better long-term memory. Gates in LSTM control the data flow, managing what stays and what goes, making them ease that handling of long-term dependencies. So in our project involved diving into data, splitting for LSTM training, and optimizing with parameters like dropout, layer count, and thickness. Its RNN is evolving into supercharged LSTMs. So I'm going to conclude in a nutshell. RNNs lays the foundation and LSTMs elevate the game by conquering memory challenges, proving to be the champions of the sequential data task. So thank you. Below, I'll be providing the YouTube link. Thank you.